Well, in the first video on aromaticity, we looked at sort of what it is, not which molecules have it. We looked at the benzene ring as the sort of prototypical aromatic system, and we said that you had to have three things to be aromatic, and the benzene ring had the greatest stability by aromaticity. One, it has to be a ring. Second, we said that ring has to be conjugated throughout, and benzene had to have p orbitals then yoked together. That's what it means to be conjugated. So at each carbon in benzene, we had to have a p orbital overlapping with a p orbital all the way throughout the ring. And then we said that we had to have so many pi electrons within that ring system. The magic numbers being equivalent to the equation, Huckel rules, 4n plus 2, where n is any whole number, 0, 1, 2, 3. So we had magic numbers of 2, 6, 10, 14. And then as we go through benzene, we counted the number of pi electrons, or electrons in p orbitals, 2, 4, and 6. So with the second video, what we'd like to do is move beyond the question of what aromaticity is and start applying these three questions that determine whether a structure is aromatic if they answer yes to each of these three. It is aromatic if it answers yes to these three. We can look at aromatic heterocyclic compounds. Heterocyclic meaning any ring cyclic that has a heteroatom in it. Nitrogen, sulfur, phosphorus, silicon. The second type of system we'll look at is an aromatic ion, whether it be cation or anion. And then annulenes, ring systems, monocyclic ring systems having more than 6 carbons, and polycyclic systems, aromatic hydrocarbons that are containing more than one ring. These are often called in an abbreviated, form, PAWS, or acronym, polycyclic aromatic hydrocarbons. So these are PAWS. These are pollutants that can come out of smokestacks, coal-burning plants, if there's an oxygen-deficient, environment. Let's remember those three questions. We have to ask any structure that we're wanting to investigate as being possibly aromatic. Do we have a ring? Is it a ring? Remember that question. If we don't have at least a ring system, there's no chance for aromaticity. Is it conjugated throughout ring? So I'm just going to say, is it conjugated in the ring? Conjugated, meaning overlapping p orbitals. So conjugated, I just abbreviated here, C-O-N-J. Conjugated in the ring. Is it containing overlapping p orbitals all the way throughout the ring? And as soon as we have this, remember, we have the divide going from the first energy shell, or row, to the next higher energy. We start to have a divide of two degenerate orbitals that can hold electrons. That can be good or bad depending upon if we fill it completely. Then last, do we, have 4n plus 2 pi electrons to go into those p orbitals that are in the ring. So let's remember that as we look at the three systems. Heterocyclic systems, which we have one here, the aromatic ions, and then the annulenes and polycyclic systems. All right, so the first thing you want to do with any, skeletal structure is make sure you draw in all non-bonding electrons. These are not shown on nitrogens, oxygens, sulfur. They're not shown, but you need to know they're there. How do you know they're there? If they weren't there, you'd have seen a charge on this nitrogen. So let's draw those in and ask our three questions. Do we have a ring? Well, of course we have a ring involving the one nitrogen and the 4 carbons. Is the ring conjugated throughout? Well, certainly for these 4 carbons, being that they are in pi bonds, each carbon being in a pi bond, we have to have sp2 hybridization all the way around for each of these carbons. So of course they have to have a p orbital to make the pi bond overlapping with a p orbital here, And this has to have a p orbital overlapping with a p orbital here to make the pi bond. But the question is, what about this nitrogen? Well, it can certainly be sp2 just to give us resonance to localization of the lone pair into the neighboring pi bond. And for that reason, he would be sp2 hybridized. But for even greater reason, if he's sp2 hybridized, the lone pair sits in a p orbital. That's very important to say, well, that since the nitrogen's sp2 hybridized, or can be at least, and with it we will have aromaticity, it will favor sp2 hybridization. It was already favored by resonance. Now it's going to be even more favored, given that this can gain aromaticity if we make this nitrogen sp2. We gain conjugation throughout the whole ring, overlapping p orbitals, all the way through. Overlapping p orbitals. Let me just see if I can. And if those p orbitals are now overlapping throughout the entire ring, we can move to the last question. Do we have 4n plus 2 pi electrons? And let's start counting. 2, 4, 6, and we're back home. That is a magic number where we can get to 6 if n is equal to 1. So we have that orbital picture that we had set in on this structure. That should come to mind. Please, you're not going to be able to always draw this type of picture. We should start to try to see them on these bond line structures or skeletals, so that we have a better understanding of what it means to be conjugated and how many and which electrons to count. Only count those that are in the p orbitals. So it was a cyclic species. It was conjugated throughout the ring, and we had 6 pi electrons. And so yes, this pyrrole is aromatic. Let's move to the next type of system where we have an ion, a positive or negatively charged species. So we can take cyclopentadiene, which certainly would not be aromatic because even though it is a ring, this carbon is sp3 hybridized. So it would not be conjugated throughout the ring. So this would be just be a non-aromatic structure. Not aromatic or anti-aromatic, but just non-aromatic. But what if we were to take this cyclopentadiene and create charges? So let's look at each of these two charges, and even the radical in between. It's not an ion, but a radical. We can look at whether they're aromatic. So let's do the, I guess, first one here, B. Aromatic, well, is it a ring? Well, sure it is. Check. It's conjugated throughout because this carbon, being that it has only 3 bonds off of it, there are no other electrons. Carbon has a positive charge if all it has is 3 bonds around it. So it has an empty p orbital. So I'm just going to sort of show it there. It's empty, but it's still yoked together with the other atomic p orbitals, which would be coming straight out of the paper towards our eye. It's yoked together, so it has conjugation. The number of electrons, though, does not come up to 6. 2, 4, this p orbital was empty, so we'll only have 4 pi electrons. So 4 pi electrons. Uh-oh. That is not aromatic. Then actually the 4n rule, then, if we set n equal to 1, this is a anti-aromatic structure. This structure is anti-aromatic. Now, with the next system, I think we can go a little faster. We have 3 bonds off this carbon. It's sp2, so that we can gain resonance to localization of the lone pair into the neighboring p orbitals. But of course, if we count all electrons around the ring system that are in the p orbitals, we're going to have an odd number. So it's going to be a non-aromatic system. Because we cannot get to a 4n plus 2 number, we can't get to that, and we can't get to a 4n number either. So just a non-aromatic structure. And this one here is just, to buckle out of that anti-aromatic state, made to twist and turn to try to avoid the anti-aromaticity. Now, the last one, we have 3 bonds off this carbon. We have a lone pair, and we could say sp3 for if maximum separation set its hybridization. But we have desire for this lone pair to spread out into neighboring pi bonds by resonance. So we can say it's sp2. The p orbital then has 2 electrons in it. The 3 hybrid orbitals, sp3 hybridization gives us 3 hybrid orbitals, are used to bond to the carbons and to the 1 hydrogen. So of course the lone pair has to be in the p orbital. So let's count that lone pair. That's 2, 4, 6 in the ring system. So we have an aromatic ion. An aromatic cyclopentadienyl anion is aromatic. Not the cyclopentadienyl cation, but the cyclopentadienyl anion is aromatic. So this would be aromatic, non-aromatic, and anti-aromatic. All right, one last one. Looking at polycyclic systems and annulenes. Let's continue to ask the questions. Is it a ring? Is it conjugated throughout the ring? And do we have 4n plus 2 pi electrons? Now we can do that for parts of a polycyclic system, or we can do it for the whole. To do it for the whole, we consider only the conjugated electrons in the outer ring. So we take a walk around the outside. Now it's obvious here that we're going to hit all pi electrons. So to see if naphthalene here is completely aromatic, not just benzene rings within it being present, but is it completely aromatic, we have to go around the outside. So going around the outside, certainly it's cyclic. Is it conjugated throughout? Well, certainly we have sp2 hybridization for each of the carbons. And if we count the pi electrons, again taking a walk here, starting here, 2, 4, 6, 8, 10, and we come back home, we had 10 pi electrons. So naphthalene would be aromatic. Pyrene, we can do the same thing, but we notice, just kind of looking at pyrene, that we're not going to count all pi electrons, because if we take our walk around the outside again, we would only count half of this pi bond that's going towards the interior. We would never, going around the outside, touch this carbon, nor would we touch this one. So you can do it a couple of ways. You can go ahead and count all pi electrons and know that you're going to subtract 2, or just count as you go around. I'll do the harder one, and maybe you can do the easier one here. So let's just count 1, because we're not counting both electrons. We're not going to see both. We're going to see, in a sense, 1 electron, but we won't count 2 because we don't touch this carbon. So 1, 3, we touched just one of these 2, so that's 4, 6, 8, 10, 12, 14. 14 pi electrons are counted as we walk around the outside. This is one of the magic numbers. So the pyrene is certainly has a ring around the outside. We could walk that ring. It's conjugated throughout. We had 14 pi electrons, and so that is one of the magic numbers, 4n plus 2, where n is equal to 3. 3 times 4 is 12, plus 2 is 14. If n is equal to set equal to 3, and we can set that. We can set that n to be any of those whole integers, 0, 1, 2, 3, 4. Just a quick note, stability of these polycyclic systems tends to increase the more you have benzene-like rings within the structure. So just to give you an example of what a benzene ring looks like and what a non-benzene ring looks like. In pyrene, we have different resonance forms, but for this resonance form, we can see this is a benzene ring, or benzene-like ring. This is a benzene-like ring, so that's 1, 2, and this is a benzene-like ring. But we certainly wouldn't count this one down here to be a benzene-like ring. We see a lot of pi bonds taking off from these carbons, but not giving us that benzene-like look within this ring. So we would say this resonance form has 3 benzene-like rings within it. That gives it stability. Last, the annulenes. We said they are just conjugated monocyclic hydrocarbons with more than 6 pi electrons. Now you would think if I walk around the ring or the outside, it is a ring. We can't have sp2. We have sp2 hybridization all the way out throughout, so you'd expect that you could just count up the pi electrons and determine if this is aromatic. We count those: 2, 4, 6, 8, 10. 10 pi electrons. 10 pi electrons. But it turns out this is not aromatic. Well, it has to do with the fact that these hydrogens here, I guess I can't really draw them. They're trying to sit on top of each other. They are sitting in the same space. So we have two hydrogens coming off of this carbon towards the interior, trying to sit in the same space. And if they bend away from each other, the whole system then becomes non-planar, and you lose your yoking together of p orbitals throughout the whole cyclic system. It has to come away from a planar conformation or planarity. Well, if you do, then you lose conjugation. So why is this not aromatic? Because we lose conjugation due to crowding, I guess. Crowding of H's. So those H's that we just talked about they're bumping into each other. It's sterically repulsive, so they are pushing away and cause the ring to be non-cyclic. All right, we're just about done. This is our last slide, just kind of summarizing where we've been. We've looked at what is aromatic, or sorry, what is aromaticity, and it really had to be tied to molecular orbital diagram to understand the Huckel rule. And we said that Huckel rule really comes out of this MO description, where if we have an odd number of p orbitals, we end with just an odd number, 1, 3, 5. But if we have an even number, like for benzene, 6 p orbitals, we get 6 molecular orbitals. The key was that on the second energy level, we start getting degeneracy, or equal energy orbitals that have to be filled. So 2, of course, 4 more, and you can kind of see then that if you add those numbers up, it's 2, 6, 10 as you fill up. That was very important. That was very different from a non-cyclic system, where we can have 3 pi bonds just like benzene. But if we have MO description of this structure, considering all p orbitals, we have to stack the molecular orbitals, the pi MOs, have to stack one on top of each other. So the electrons, all 6 of them, stack on top of each other. We're over here, we can keep the energy low because we stack in the second energy level 4 electrons. So that was the key difference between aromaticity and a non-aromatic system. And then we applied our rules to different types of structures. Let's just review those for these 3 heterocyclic systems. We have, if we consider the whole of this Kendall lever, we can look at its aromaticity of the whole, not just the part. This is a benzene-like ring within the system. This would be another aromatic ring within the system, having 2, 4, and we count only 2 of these electrons. We'll talk about that in a little bit. Let's look at the whole of it. Well, certainly it's cyclic all the way around. Is it conjugated? Well, we have to set this to sp2 to even have a chance. Not both lone pairs can sit in a p orbital. One would sit in a hybrid orbital sticking straight out, and one could sit in that orbital coming out towards us and into the plane of the paper here. So we put 2 in a hybrid orbital and 2 in a p orbital. Count those 2 then, not both, just these 2, not this pair. 2, 4. We're going to go ahead and count this because we're going to see it here, or we're going to see both of the electrons. So 2, 4, 6, 8, 10. It is conjugated throughout, and we have 10 pi e's. So this would be aromatic. Let's do the other, and we'll be done here. The oxygen again, we cannot count both if it's sp2. We have to put one in a lone pair in a hybrid orbital, because you always have 3 hybrid orbitals, sp2. Two are used for bonding. One has to be used to hold the lone pair, and the other lone pair is in a p orbital. So 2, 4, we don't count this lone pair because it sits in an sp2 hybrid orbital. We're only going to count the pi electrons. 2, 4, 6. So it's conjugated. We have 6 pi electrons. So it's also aromatic. Let me just review that again. It's a cyclic species. We can set this oxygen to sp2 hybridization. We have a p orbital that can hold one of the lone pairs. P orbital here, p orbital here, p orbital here, p orbital here because of pi bonding. And then so it's conjugated, so we count the electrons. You can't count both lone pairs on the oxygen, just one lone pair. You don't count the lone pair on the nitrogen because it's using its p orbital to make this pi bond. This then cannot be in the p orbital. The lone pair on the nitrogen has to be held by something different, an sp2 hybrid orbital. And then, of course, the pi bond here. Let's move one last time slowly through this and we'll be done. Let's put the lone pairs in for the nitrogens. Now notice, only this nitrogen here on the bottom right is not in a pi bond. It's the only one wherein we will count these 2 electrons because this nitrogen will be sp2 hybridized, but the lone pair cannot sit in a hybrid orbital because we have 3 bonds off this nitrogen. One to the carbon here, one to the carbon here, and one to the hydrogen here. So you've used all your sp2 hybrid orbitals. This must sit in a p orbital. But no other lone pair on a nitrogen is going to be counted because it's not able to be used in the pi bond. The pi bond is here, the lone pair is here. So we don't count it. 2, 4, 6, 8, 10, because we're going to see this from both sides. 2, 4, 6, 8, 10. So we had a ring around the whole thing. We made it conjugated throughout by setting this to being sp2 hybridized, and of course we counted 10 pi e's. This is aromatic. All right, that's a long video, about, I guess, 20 minutes long. Hope that helps you get started on how to tag structures as being aromatic. Bye-bye.